Ashot Minasyan, who's going to tell us about virtual retractions in graph of groups.
Thank you very much for this opportunity to speak here. And I know this is the third talk of the morning session, so everybody is a bit tired. I'll try to give an elementary talk, and hopefully you'll see that I taught a lot of linear algebra for the first years in the past 10 years, so finally I had an opportunity to use my linear algebra in research. So it should be, there will be some algebra, very elementary geometry as well. I should say this is a joint work with Jon Meladet, who is a PhD student in Southampton. So, okay, so let me start with recalling the basic things. So what's a retractions? So a subgroup H of a group K is a retract. Well, if there is a homomorphism from K to H, which is identity on H. The identity map on H, right? So this is the standard notion, and equivalently, so this means that your K splits as a semi-direct product of the kernel of this homomorphism with H. So it's just a different way of saying your group splits as a semi-direct product with this subgroup, with some normals. Okay, so on the virtual retract, well, it's a retract of a finite index subgroup. So a finite index subgroup in G, such that H is contained in K, and H is a retract of K. And the notation is, perhaps I will use it. I put VR subscript. Okay, so far so good. So why study virtual retracts or retracts in general? In fact, in geometric group theory, you probably have seen these appear quite often, mainly because this is an algebraic condition. Being a virtual retract is very, it's just a group theoretic condition. There is such a homomorphism of a finite index subgroup, which is the identity, or in other words, it splits, a finite index subgroup splits as semi-direct product like this. But it has lots of applications, not only to algebra, but also to the geometry. Right, so these are elementary facts. If G is finitely generated or finitely presented, and H is a virtual retract, then H is also finitely generated. Well, that's kind of obvious, right? G is finitely generated. Every finite index subgroup of G is finitely generated, and H is an image of a finitely generated group, so H is finitely generated, right? This is you can also show that the virtual retract is always finitely presented of a finitely presented group, but moreover, H is quasi-isometrically embedded is a more geometric property, right? So, in fact, not only is QI embedded, in fact, well, if you have a retract of a group, if I take a generating set, any generating set here, and then I consider the generating set S union phi of S, this is again a finite generating set, but in that generating set, phi becomes basically, not only it will be the identity of nature, it will be the isometry between the embedding of H in G and itself. Just because it's a retraction. It's an easy exercise. So it will just be isometry on the nodes with this finite generating sets. Okay, so, right, so this is one reason why people care about it. The retract is always nicely embedded, and therefore it will also inherit lots of geometric properties of the group. Another reason why people care about virtual retracts is the following, also very well-known fact. If G is residually finite, and H is a virtual retract, then H is closed in the profinite topology. Or separable. So this profinite topology is a topology that you can now any group. The basic open sets are just cosets to finite index subgroups, and G is residually finite if and only if the trivial subgroup is closed in this topology. And alternatively, it just means it's equivalent to saying H is equal to the intersection of finite index subgroups of G containing H. Right, so this is equivalent to saying. So in some sense, you can approximate your subgroup H, your virtual retract, by finite index subgroups. And this is, again, a very useful property. In fact, in the previous workshop about profinite rigidity, this was, I mean, this really is an important statement. You use it all the time. And if you know something is virtually retract, it does give you very strong control over profinite embedding. Okay. So conversely, I mean, this is the power of geometric group theory. So you have these statements, and I mean, let's say, look at your favorite finitely generated group, or finitely presented maybe, coming from geometric group theory. Look at its quasi-symmetrically embedded subgroup. You can ask, is it a virtual retract? And in geometric group theory, this is actually often the case. So one of the famous theorems, I will just probably call that theorem. So this is due to Haglund and Weiss. So what they proved, so they defined this class of virtually compact special groups, which is quite a wide class, and it's there are lots of results that well-known groups belong to this class, and they proved that every quasi-convex or QI embedded subgroup of a virtually compact special hyperbolic group I have to be careful. Of a compact special hyperbolic group is a virtual retract. Unfortunately, this is unknown for virtually compact special. So compact special meaning it already sits inside the rectangle arch subgroup as some convex or compact. And virtually it has a finite index. Unfortunately, this property of being a virtual retract is not always stable under going up by finite index. This is minor problem, but I mean it's still an amazing amazing result where the geometric information gives you a very strong algebraic control for me. Right? Okay, and there are actually similar statements in other parts, like I think it's also true in the free nilpotent groups that every QI embedded subgroup is a virtual retract. This is a very different world, but it's still true in them. Okay. All right, so here's the definition. Hopefully everybody will remember it. So a group G has property VRC, so virtual retractions onto cyclic subgroups, C for cyclic, if every cyclic subgroup is a virtual retract. Okay, so this property was defined by Long and Reed. I don't think they called it VRC, but then you can define more general properties. Long and Reed also defined the property LR, which means local retractions. Every finitely generated subgroup is a virtual retract. That's much, much stronger here. I just want to look at cyclic subgroups. That's not that restrictive, actually. So, for instance, well, examples. Okay, so actually the most important examples are finitely generated virtually abelian groups. Maybe most basic examples. I mean, this is actually non-trivial, I would say. It's easy to see that the free abelian group is a virtual retract, because if you take any element, if you take any element, any cyclic subgroup in the free abelian group, well, it's normal. So therefore, it has finite index in a direct factor, in an element of a free basis, and then there is a homomorphism to Z, which kills everything else. So you just your subgroup is mapped to a finite index subgroup of that image. You pull back the finite index subgroup to the whole group, and you get something that retracts onto your cyclic subgroup. But I mean, for virtually abelian, you need to do some work, but it is not hard. Okay. Second examples, all virtually special groups in the sense of Haglund and Wise. Here I do not restrict to compact special. So this means basically virtually subgroups of rags. Right-angled arcing groups. So here you don't need to restrict to compact special. In fact, this property, it's easy to see that this property always goes down to any subgroup. If you virtually retract onto any cyclic subgroup, that any subgroup containing that cyclic subgroup will, you just take the restriction of the retraction and it will work. So it's obvious to see that it always goes down, and in fact, here you just, take any subgroup of a rag. The fact that it has VRC, this says Hagen and Wise indicates if you remove the virtually plus myself, if you do put the virtual, well, what I proved is that VRC goes up by finite index. It is actually stable under commensurability. So, okay. So this includes many of your favorite groups, like virtual surface groups, virtually free groups. What are your other favorite? Oh yeah, pi1 of hyperbolic three manifolds, closed hyperbolic three manifolds. These are all here.
Cancellation.
Not by my results, by the big machinery that was developed by Haglund, Weiss, Nagel, and many other people. So, okay, so of a different flavor, here's an example. So reef products of the form so where A is abelian, finally generated abelian, and B has VRC. Okay, so what's an example? For instance, your favorite Lamplighter groups, or just Z reef Z, they are of that kind. So this is a different type. They are not virtually special. These guys contain very big torsion, but VRC is fairly basic. Okay, any questions so far? Okay, non-examples. So what doesn't have VRC? Well, anything that is not cyclic subgroup separable, because remember I mentioned this fact. If you're a retract of a residually finite group, then you're closed in the profinite topology. So if you have a subgroup that is not closed in the profinite topology, a cyclic subgroup, then you won't really be VRC. So any group that isn't cyclic subgroup separable and what are the basic examples, or is not residually finite for that matter. So of course the Banzlag solitar groups, the non-Euclidean ones. Non-Euclidean means the modulus of M is different from the modulus of M. They will not be. I mean, these are basic H&M extensions of Z, right? And as long as this is true, they will not be cyclic subgroup separable, so they cannot have VRC. Another set of non-examples are if a virtually polycyclic group is VRC, then it's virtually abelian. Okay. This is the result of mine. I mean, it's not too bad, not too difficult, but it sort of restricts. These are solvable groups that do have VRC. They're metabelian groups that do have VRC, but they're not virtually polycyclic. But once you, if you look at solvable groups that are virtually polycyclic, you cannot have VRC unless they're virtually abelian. So, for example, take your favorite nilpotent group that is virtually abelian, the Heisenberg group. That's my favorite nilpotent group. The Heisenberg group over the integers, that's also polycyclic. And of course, that's not going to have VRC. So, all right, so I don't know how to denote this. Okay, so in some sense, this is already an indication to me that the groups coming from the non-positively curved world in geometric group theory, so virtually abelian, virtually special, have VRC. Once you start messing around with virtually polycyclic groups, this fails immediately. So in some sense, it's a feature of non-positive curvature for me, this property. It's an algebraic feature. Okay, so yeah, so there are various stability properties. So what are known stability properties of VRC? So it's the closed undertaking direct products, arbitrary direct products, restricted. It's closed undertaking free products with amalgamation over finite subgroups, origin and extensions with with finite associated subgroups. It's closed undertaking graph products, and that's how you can prove that virtually special groups have VRC. So it's closed under many sort of, again, many of the constructions, the standard constructions we use in geometric group theory. Okay, so I want to discuss when is this closed under, well, graphs of groups. Before I do that, let's see. Okay, before I do that, I probably want to state a proposition. So okay, MM will always stand for Bernadette and myself. So okay, so the proposition is the following. The following are equivalent for group G. The first property is just G has this property VRC. And the second property, so VRC can be basically characterized as a sort of a residual property as follows. For every G in G, there is finitely generated virtually abelian group P. And the homomorphism from G to P such that the restriction of phi to the cyclic subgroup generated by your element is injective. So this just says your group, in order to have VRC, it will have lots of virtually abelian quotients. Lots and lots. For every finite or infinite order element, there must be a virtually abelian quotient which sees the order of your element, which is injective on the cyclic subgroup generated by this element, right? So this is a kind of a residual, I mean, it's a residual property in that sense, right? Approximation property by finite generated abelian groups. And in some sense, it's nicer to work with because, you see, if you look at the definition of the VRC, which is somewhere
Top left. Very top.
left board. Left board is there, but VRC is here. Okay. This says about homomorphisms from finite index subgroups to Z, right? To finite index subgroups to, well, cyclic groups. But, I mean, this can be alternatively said, you look at homomorphisms from the whole group to virtually abelian groups. It's equivalent, right? And this is a useful point of view. Okay, there's a third item here. Okay. For every finitely generated virtually abelian subgroup H in G, there is a homomorphism. So there is a finitely generated virtually abelian group P and phi from G to P such that phi to H is injective. So not only you can make it injective on all cyclic subgroups, actually you can make it injective on all virtually abelian subgroups, finitely generated. Okay. All right, so if you look at this statement here, I mean, this, you can compare this. If I added here that the virtually abelian group P is locally indicable, meaning every finitely generated arrow, in this case, every subgroup surjects onto Z, then this would define the reverse property. So VRC, so this sort of shows that reverse implies VRC. If you know what reverse is, if you don't, ignore this. So this is a property that is useful for virtual fibering. The other way, it's not true. So the other way, you can give examples where it's not even virtually reverse. Okay. Much slower than I thought I would be, okay? So I want to, okay, so C. So let's look at the following class C. So C is class of all fundamental groups of finite graphs of groups with virtually abelian, finitely generated virtually abelian vertex groups. Okay, so just take your, okay, so what does this include? We've seen quite a few groups like this. So for instance, I don't know, any H&N extension of Z to the N, or an amalgam of virtually abelian groups or anything like that will be in this class. So this class is quite actually big, and it pops up in a lot of work in geometric group theory. So for instance, it contains all tubular groups of Y's. So what are the tubular groups? Well, the tubular groups, just by definition, are these guys, where the vertex groups are Z squared and the edge groups are Z. Okay, so it also contains all the generalized Banach-Solitar groups, whatever you like. It could be just graphs of cyclic groups or graphs of ZMs with ZM vertices with finite index H groups. So it's a pretty big class, and we study it all the time in geometric group theory. Okay, so here is a theorem, a characterization of property VRC for this class. Okay, where do I want to put it so that I don't erase it? Here, actually. Why not? Yeah. Put it here. Okay, so theorem B. So let's look at any group in this class, right? Then again, the following are equivalent. Actually, if you look at this proposition A, so it characterizes, VRC as this approximation property. Now look at the second condition. It says G has VRC if and only for every virtually abelian subgroup there is such a homomorphism to a virtually abelian group P injective on that subgroup. So in fact here, basically we say that it's enough to consider vertex groups. So again, G has VRC. For every, there is a finitely generated virtually abelian group P and a homomorphism which is injective on every vertex group, or yeah, vertex group of your graph of groups decomposition, right? So basically, you just need to look at this. You just need to look at the vertex groups. If you find one, in fact, it's enough to show actually that each vertex group individually is a virtual retract, which is the same thing. And the third condition, is the sort of, okay, well, for me, virtually abelian groups are very nice. But there are even nicer, in some sense, virtually abelian groups that we call Euclidean bifinite. So, okay, so the same thing, there exists a Euclidean bifinite group P such that this holds. The same conclusion, yeah? There is a homomorphism from G to P, injective on every vertex group. Now let me define what Euclidean bifinite means. So, a Euclidean bifinite group is any group of the form Rn, semi-direct, Q. So Rn is Rn, right? Where Q is a finite group. Acting on Rn by Euclidean isometries linearly. So namely, you have a representation from Q to ON. This is how it acts. Okay? And that's actually actually, this is equivalent to that. Why? Because obviously such a group, Euclidean bifinite group, is just by definition, it's Rn bifinite, so it is virtually abelian. And any virtually abelian group, finitely generated virtually abelian group, can be embedded in one of these. I think this is a Faulkner fact, so it's not difficult to show. But why do I care about this third thing? It's because this allows us to use very elementary linear algebra or geometry to detect BRCness. Okay, so I want to give an example. Oh yeah, so actually what this says for geometric group theorists, Rn acts on itself by translations. Q acts on Rn linearly. So the whole group acts on Rn by isometries with a finite linear part. Right? Most of them are just translations, and then the finite group of subgroup of ON. Okay, so this action is helpful. Okay, so examples. Okay, so I look at this family of groups on this board. Okay, you're not supposed to see what's about. This is the presentation. So what is this? This is, you see, A, B. There are 4 generators. A and B commute. So this is a free abelian subgroup of rank 2. Then S and T are the free letters, so they will be like H and N extensions. So S conjugates A to B, very easy. T conjugates B to some element, arbitrary element, B to the K, A to the L. Right? So this is a double H and N extension of Z squared with cyclic H groups. Okay, so let's look at this family. So I want to characterize when do these have VRC using the theorem? And I'm really slow, so okay, but this is the main point. Why do we care about Euclidean by finite groups? Okay, so I'm going to assume for simplicity, actually I'm going to assume L equals 1. So A commutes with B, S conjugates A to B, T conjugates B to the K. Okay, for simplicity, just to simplify the calculation, let's assume this. So suppose G has VRC. Right? This is in our class C, so our theorem applies. Where's the theorem? And then you probably cannot see it anymore. Okay, this theorem applies. So we should be able to find the Euclidean by finite group, right? So this admits by the theorem there is an action of this group G on Rn via these isometries, so via the action, the natural action of the Euclidean by finite group. So, okay, so if M is the order of your finite group Q, then okay, so we have a homomorphism. Should I do a okay, A to the M and B to the M act by translations, right? Because they are mapped into Rn semi-direct Q, then the mth power will be in Rn, so it's action by translations. Some vectors U and V in Rn. Okay. Moreover, this action will be, it's a faithful action of the AB plane because it's injective on the AB. That's the condition, right? I mean, it has to be injective on the AB. AB is the vertex group here. So it's injective on the AB. Well, these conditions now tell us, see, it's an action by isometries. The fact that A is conjugate to B means A to the M will, of course, be conjugate to B to the M. And because it's an action by isometries, the norms of U must be equal to the norm of V. The Euclidean norm. And moreover, this condition here tells us that the norm of U plus KB is also the same because that's conjugate to B. Okay? And A and B commute. So, okay, so this is the geometric information I extract from these relations. A is conjugate to B. This means S sends U to V. S acts by isometries. Therefore, it preserves the norms. Okay, well, this is after renormalizing. I mean, just rescale the metric. You can assume this is 1. They are all norm 1. Okay, after a rescale. So what does this tell us now? If I square this, so this will be 1. Now this is where my linear algebra background comes in. I use the fundamental theorem from planar Euclidean geometry, right? This is the norm of U squared plus 2k norm of U, norm of V times what? Cos alpha, where alpha is the angle, right? Right? Theorem of cosines, which I prove in my linear algebra using vectors. Great. But these are all 1, remember? So this means 1 is equal to 1, oh, and I forgot k squared here, right? 1 plus 2k cos alpha plus k squared which is equivalent to saying either k0 or cos alpha is minus, what is it, k over 2, right? Immediately from here, I mean, cosine cannot have values exceeding 1 modulus, so in particular, modulus of k must be at most 2. Okay? All right, easy? Okay, so now you should tell me what happens if modulus of k is equal to 2. I'm always asking my questions when I lecture linear algebra, right? Then what? Zero. Alpha is 0 or? Thank you. Well, remember u and v are two vectors of the same norm. If the angle is 0 or pi, they are either, they are either equal or minus each other. But this is impossible because this means that a to the m, the image of a to the m will be equal to the image of b to the plus or minus m. But this is a contradiction to the fact that our homomorphism was injective from the base. Right? It cannot be. So this is impossible. On the base group, right? AB. So therefore, in fact, it must be less than or equal to 1. Okay? So we've reduced our infinite family to actually only finitely many cases. I mean, this is like right? And in each of these 3 cases, you can actually explicitly give the Euclidean bifinite group. So for instance, if k is minus 1, we look at this equation, and we say cosine alpha is 1/2. Right? Okay, great. Alpha is what? 60 degrees. I always tell my students, do not use degrees. It's radians. Okay, fine. You didn't know my rule, but. Okay, here is the picture. So I can always, I'm going to choose my u, the vector u, to be 0, 1 or 1, 0. The other vector will be at pi over 3 from it, right? And let's see, so what does this say? So this will be, u will be the image of A. So A goes to u, B goes to V. And the third relation, when k equals -1, says B, so this says, well, the right-hand side, B is conjugate to B inverse A. So TBT inverse is B inverse A. So this means this third vector is just, it will go to U minus V, right? And again, this is something I teach my linear algebra students straight away. Well, U minus V is Is it, which one is it?
Downwards, yeah.
Okay. Why did I draw it upwards? So I made a mistake now. Okay. Yeah, I do see one. Okay. Well, it's going to, I have to center it. So this is u minus v. I have to draw it here. And now you can tell me, I mean, this is also pi over 3, right? So this is also u minus v. Now you can tell me where can I send s and t. What will be the isometries in ON? What will be the isometries that it must send u to v? That's the first relation. A goes to, you know, s, A, S inverse is b. So s must send u to v. And the second relation says t must send v to u minus v. Unless we made a mistake somewhere. So what do I take as s? Rotation by pi over 3. And actually, and if I want to take that, v goes to minus v, well, that angle is minus 2 pi over 3. But all of it is inside the cyclic group generated by the rotation by pi over 3, which is C6, right? So we have witnessed our fact that this group has VRC in this group, okay? And you can do the same, very easily the same in the other two cases. Okay. You get only a finite family here, only, so, oh yeah, so this is similar now, I can come back. So G has VRC for GKL, actually it's similar, and the answer is here, if I find it. If and only if KL, they cannot be both 0, but anything else in 0 plus minus 1 works. Again, there's only 8 groups, well, 8 presentations actually, and some of these will be isomorphic. There's only 8 groups like that. So you'll think, okay, there are only finitely many, right? Maybe it's just, oh, you know, okay, why bother? But actually, I can look at these groups. So I'm going to look at, again, double HNNs of Z squared, the usual stuff, and the first relation is the same. I just like the norm of u to be equal to the norm of v. The second relation is arbitrary. Avoiding the obvious exceptions when one of them is 0 and the other isn't. So there I suspect there are infinitely many groups. And the reason why I suspect this, well, I haven't made the explicit calculations, but the point is, it's very nice to be a visitor at Newton Institute because you get to share offices with people. And my office mate was Giles Gardam. And then I knew that you can approach this question if you look at the theorem which I've used the third equivalence for doing it by hand, the geometry, but I mean, for more complicated equations, you know, I don't know how to solve them. But the second point is actually a very algebraic one. And in fact, all it says is that, you know, if you have a homomorphism to a virtually abelian group which is injective on your vertices, well, you take the virtually abelian group, you take the finite index subgroup that is z to the n, you pull it back to a finite index subgroup of your group. This finite index subgroup will see every vertex group in its abelianization. It will just see its intersection with the finite index subgroup will inject into the abelianization. And this is very easy to check by computer, by GAP. And that's what I asked Giles. I said, do you know how to do this in GAP? He said 30 minutes. And then he did that, And he came back and said, no, it took me longer, 34 minutes. So he programmed, and he found, I think I'm not lying, 408 examples with VRC. When you limit all of the exponents, so modules of k, at most 5, and you limit the indices up to 6, indices of the finite index subgroup, because you can just list all the finite index subgroups using your presentation, and then you can check, does it inject the abelianization or not? It is all implemented in GAP. So I suspect this will be an infinite family. And it's using this other thing. So both computers and geometry are useful. To come back to Ala's talk yesterday. Okay, so any questions? Like I said, it's actually very elementary to check. If you give me your favorite group from C, it may be very elementary to check if it has VRC or not. Well, you could say maybe only few have VRC, which I agree. Unfortunately, many do not, but all the virtually special will have. And again, there are quite a few virtually special groups that are tubular groups. So Weiss and Woodhouse produced quite a lot of them. Okay, trying to find what's next. Oh yeah, so consequences. So what are the consequences of this property? This is a very algebraic property on the nose, VRC, but there are consequences. So proposition C, if G is in this class C, it has VRC, then G is cut 0. So it admits a proper co-compact action on a cut 0 space. And in fact, you should have recognized what I was doing there, with the norms and the angles. This is what you do usually to show that some group is not cut 0, right? Precisely. So this cut 0 is a geometric condition, but it is implied by VRC in this case, in the class C. Oh yeah, so of course this has lots of applications. Being cut 0 implies you have solvable conjugacy problem, you are bicombable or semi-hyperbolic, you have at most quadratic Dane function. All of these things genuinely fail in C. In C there are counterexamples like the famous groups of Brady and Brightson, the snowflake groups that Martin talked about, are precisely double H&M extensions of Z squared with cyclic H groups, similar to JKL, and they have arbitrarily bad, essentially, Dane functions. So they're very far from being cut 0. Okay, what are the other properties? Proposition D. Again, here I'm going to restrict to tubular groups. So tubular group is a special subclass. So it's fundamental group of Z squares. Vertex groups are Z squares, and H groups are Z. But I mean, all my examples, JKL, are precisely tubular groups because they are fundamental groups of one vertex Z squared, the base group AB, and two edges, cyclic edges, loops at this vertex. G is tubular and has VRC. Then G, again, it's a very strong restriction on algebraic structure. E is virtually, so it has a finite index subgroup, finitely generated free by cyclic, by Z. So it's there free by cyclic. And this uses the work of Jack and the work of many other people. So Jack Button basically characterized when a tubular group is free bicyclic, and we can do the up to finite index. This will work here. Okay. Yeah, so there is an example, the famous example of a free bicyclic tubular group that doesn't have VRC. Well, this is the famous example of a free bicyclic group that isn't cut zero. It's due to Gersten, right? Again, this is a double H&N extension of Z squared with two cyclic subgroups. And Gersten proved that this free bicyclic group is not cut zero, therefore it cannot have VRC. And it is also therefore not virtually special. So one more application. And this here is actually in the appendix to our paper. So this is joined with Xiaolin Wu and Shen-Ku Ye. And we notice here that a tubular group G has VRC. So VRC is always implied. All virtually special groups have VRC, but for tubular groups this is equivalent. It is equivalent, so this direction is always true for all groups. The opposite direction is true for tubular groups, and this uses the work of Woodhouse, who showed, well, if you have a tubular group that admits a free action on a finite dimensional cut-zero cube complex, then it is virtually special. And we produce a finite dimensional cut-zero cube complex here, a very boring actually one. I mean, I never before produced any special cut-zero cube complexes, but here the cube complex will be very boring. It's just the product of the Basser tree with the Euclidean space, with the cubulation of a Euclidean space, which counts from your homomorphism onto Zn. That gives you an action on Rn, and then you have the product. You have the product action, and that will be free on the vertices, and it will be a finite dimensional cube complex. So by Woodhouse, this is virtually special. So the reason why actually I managed to convince Giles to write this 30-minute program is because I didn't say VRC. He doesn't know what VRC is probably. But I said these groups have this condition, even only they're virtually special. And he is actually interested in snowflake groups and in virtual specialness. So for him, yeah, so this is actually, I mean, one could think, oh, maybe this is disappointing, you don't get anything new. But for me, it's actually the fact you can check this fairly easily. Woodhouse gave some sort of an algorithm, but Jack knows it's not easy to check. Not easy. This is very easy. Right? By computer, it's very easy to check. Right? You just go over all finite index subgroups, look at all maps. Right. I had some more results planned, so there are more results in this direction, but I ran out of time, so I'll stop here.
Are there any questions?
Maybe this is one of the future results. I don't know. Do Leary-Minasyan groups have VRC?
No, the ones that we have are not even Hopfield, right? I mean, they are, VRC is a very strong, like it implies cyclic subgroups are separable, in particular residually finite, so the ones that it's an open question whether there is one that is residually finite, but our groups will never have, because you have this Z squared that is commensurated, but I mean, this Z squared would have to be virtually retract, and I think if you add it to commensuration, it probably forces it to basically the matrix to have finite order.
Okay.
Can we have the hidden list?
Oh, yeah, oh, sorry. Right, the hidden list. Yes, I forgot about it. Yes, thank you for reminding me. So this is actually well, we can check, so this implies that, right? But with the same geometric argument, actually check that if this has cut zero property, then the same argument says that it also works backwards here. This is equivalent because these are tubular groups. So in particular, this is also equivalent. So all the conditions here are the same. Virtually free bicyclic actually is interesting. So you can be virtually free bicyclic without being VRC. And if I find my... Okay, so the condition here is, again, very similar. Either the modulus of K equals the modulus of L equals 1, or, now we do have a finite infinite family here, K plus minus L equals 1. This gives us an infinite family. We can characterize this. I mean, in this case, they do not have to be VRC. If K is greater than 1, they won't be. But you can still use very similar methods to just check that. You can also characterize when they are free bicyclic, and this gives you only if and only if K plus L is 1. Again, in infinite family. Virtually free bicyclic, you get more.
If you have no more questions, let's say.